Я хочу вибачитись, тому що я збирався свою частину лекцій вести українською, але серед нас десь є студент-німець. Тому в якийсь момент, коли він прийде, я перемкнуся на англійську. Якщо будуть якісь питання, щось незрозуміло і так далі, і таке інше, будь ласка, зупиняйте, питайте, якою б мовою питання не було і якою б мовою я не розмовляв. Отже, ми зараз повернемося на пару кроків назад від того, на чому закінчив Юваль. Юваль ввів слабкі вимірювання і пішов розповідати, як слабкими вимірюваннями керувати квантовими станами. Ми повернемося на 2 кроки назад. Ми ще раз поговоримо про слабкі вимірювання і поговоримо про інший цікавий аспект, про те, що можна ними робити. Отже, давайте почнемо з того, що є таким парадигматичним квантовим вимірюванням. Який дослід сказав нам, що з вимірюванням у квантовій механіці є щось нетривіальне?
Квантовий досвід тіла?
Який?
Квантовий досвід тіла?
А про що це?
Ну, коли в нас частинки можуть, коли ми намагаємося спостерігати через очі, вони пролетіли, проявляти скулярні.
Гаразд, але це нещодавній досвід. А я кажу про досвід, який було поставлено приблизно 100 років тому. Я почну малювати. Є ідеї?
Штерна-Герба?
Так, Штерна-Герба. Тобто в нас є якась зона, в якій є градієнт магнітного поля. Ми посилаємо частинки усіх можливих спінів і очікуємо, що... I'm switching to English. Great. Right, so we're sending particles of all spin directions. We have a gradient of the magnetic field, and we expect that according to the spin projection onto the z-axis, the particles will shift upwards or downwards. But they are all sorts of spin directions, so we expect something smooth, some continuous distribution. Instead, what Stern and Gerlach observed in their experiment was that they had 2 sharp lines. Not a continuous distribution, but 2 sharp lines. And that tells us that when we measure spin projection onto some axis, we don't get a continuous numbers, a set of continuous possible numbers, continuous outputs, as it would be in classical physics, because the projection can be anything. Instead, we get, for spin 1/2, we get 2 values, for spin 1, we get 3 values. And that tells us the basic properties of projective measurements in quantum mechanics. Now think of the incoming beam. It has some width. I send particles, but they can fly here, or here, or here, or here, like this. And they get deflected according to their spin projection. And I have 2 beams. And if the shift between the 2 beams is larger than the beam width, I can definitely say, here I have particles of spin down, here I have particles of spin up. That's it. But if the beams overlap, and I see, okay, my particle flew around here, what does it tell me? It tells me that probably it was spin down, say 80% probability it was spin down, but there is a chance, 20% that it was spin up. So I don't learn everything about the spin projection. I learn the information only probabilistically. And that's exactly the weak measurements that Yuval was talking about. And instead of considering this complicated model, because there are all sorts of problems here, for example, it's not possible to have dBz over dz non-zero, but dBx over dx or and dBy over dy zero, because divergence B has to be zero. So all sorts of complications. Therefore, we want to consider a simpler model, which nevertheless captures these features. And this model is von Neumann measurement model, or some call it problem. As in any measurement model it should be, we have a system that we're going to measure and a detector. The detector is going to be a continuous coordinate. So a particle with some coordinate q has some momentum p. P and q satisfy canonical commutation relations. And we can introduce the eigenstates of q. And I will denote detector states as D. This is going to be my detector. So it looks pretty much like here. My particle can have a coordinate here, and the measurement is going to shift the coordinate. What is my system? I can keep the system general. I have some observable A. The system states will be denoted as psi. And I can introduce the eigenbasis of A. And I can decompose any system state in this eigenbasis. Finally, I need something that tells me how my detector interacts with the system. And since I'm not modeling any real system, but instead I'm inventing a model that would mimic these properties, I can write whatever I wish, and what I wish is going to be this interaction in autonomy. It has some coupling between the system and detector. I'm going to put the coupling to 0 except for some finite interval of time. And this is going to be my interaction in autonomy. So within this model, until t equals 0, nothing happens. Then at t equals 0, I'm turning on the interaction between the system and detector. And at time t equal capital T, I'm switching it off. Which means that I have the initial state of my system and detector. I have some psi initial times d initial, detector initial state. And after the system and detector interacted, my final state is going to be the t exponential of integral 0 to capital T dt, h interaction of t times psi initial. Everyone fine with this expression? Any questions about this evolution? No questions.
What are the reasons for writing the Hamiltonian
because it will give me the result
form?
I want.
Hmm?
Because it will give me the result I want.
Mm.
You'll see it in a couple of minutes. But my Hamiltonian commutes with itself at all time moments, so I can rewrite it as e to the minus I lambda a p psi initial d initial, where lambda is the effective coupling step. This tells me how strong my system and detector were coupled and for how long time. So what I want to know is, what does this operator do to my system state, to my detector state? So I want to know what that operator does. Let me do a preliminary exercise. I want to consider just the action of this operator on the detector. So I will replace the system part with a number. So I have e to minus I alpha p, and I will take a simple detector state, q. Can anyone tell me what it's equal to? What does this operator do to my
Derivative.
Yeah, so p is derivative.
It's v.
Yeah, so it's a translation. This is q plus alpha, I think. Let me check.
Minus.
With a plus. With a plus, and I'll tell you why. Because p acts as the derivative onto the wave function. P equal to minus I dq. This is a shorthand. This actually means the following. This actually means q p psi is equal to minus I dq q psi. This way it acts on the wave function. If I want to know how it acts on the states, I can do two things. I can either integrate this wave function with q states. I know how it acts on the wave function. It shifts the wave function by minus alpha, so I do a variable change. It will shift my q by plus alpha. There is a better, a more universal way of checking that. I can calculate this. In the lecture notes I send out, I put it onto the Mendeley group. You'll find out how to calculate this, but the answer is that this is alpha to the I alpha minus. And what it means, this commutation relation, did I write it down correctly. Yes. So what this commutation relation means is it's simply that q e to the minus I alpha p is equal to e to the minus I alpha p times q plus alpha e to the minus I alpha p. Now, if I put some q state here, and I put some q state here, the left-hand side is q times e to the minus I alpha p times this q. So this is some state. I'd like to know what the state is. This, I can actually act upon. Here I have q acts, I know how it acts. So I have e to the minus I alpha p q plus alpha times q. So it's q plus alpha e to the minus alpha p q. So I know that this eigenstate is an eigenstate of q with the eigenvalue q plus alpha, which means that it's q plus alpha. Is everything fine about this? Any questions? Anyone not convinced that this is correct? Okay. You'll have to sit down and derive it yourself later. So I know how this operator with the momentum in here acts onto the states of detector. Now I'm ready to come back to the more complicated problem, how this operator acts onto the states of the detector and the system. So I have e to the minus I lambda a p times psi initial times d initial. This state, it's sum over a, ca, a. So I can write like this. And this is the detector state. A is an eigenstate of A, so this acts with an eigenvalue of A. B does not act here, so it keeps being an operator. So I can write this as sum over A, Ca, A to the minus I lambda A, P, D initial. Now, what is the detector state? The detector state is a superposition of different coordinate states with some wave function. And I know how this operator acts on them. It shifts these q. So this is equal to sum over A, integral dq, Ca, A, phi of q, q plus lambda A.
Excuse me, maybe you have a better pen?
I'm trying to find one. So I have shifted this q. I'm going to change the variables. I can change this integration variable. What I get is the following. So this is the result of the interaction between the system and detector. So my psi final is equal to, this was equal to sum over A integral dq CA 5Q A Q. And this is equal to sum over A integral dq CA 5Q minus gamma A Q. So what does it mean? I prepared my system in some state. I prepared my detector in some state. I let them interact according to this Hamiltonian. And as a result, depending on the system state, the detector state was shifted. So that's exactly like the Stern-Gerlach experiment. I can calculate now what's the probability of measuring the detector in some state Q, with some coordinate Q. How do I do this? The probability density of Q being equal to Q naught, it's simply this, that the detector is a coordinate Q node, and the expectation of the delta function of this is going to give me exactly the probability density that the detector is in this state. So I take this final state, I can write sum over A and prime integral dq prime CA star.
So what is psi alpha? What is psi alpha?
It's psi f phi.
And there is also psi f. And there is also psi f to the on the
This is exactly the same psi f.
On the central desk, the psi f delta function psi f.
Yes.
It looks strange because.
Okay, so suppose I have a state with a wave function phi of q. That's my state. What's the probability that my particle, what's the probability density of my particle being at q node? I think you'll agree that the probability density is going to be psi of q node absolute value squared. Agreed? Now let me calculate the following thing. This is equal to this. Then this Q acts onto either of these eigenstates. So this can be replaced by delta of Q minus Q node times Q prime. And this is the delta of Q prime. Now I integrate over Q prime is equal to Q. I integrate over Q is equal to Q node. And what I'm left with is exactly this. okay? So the correct way to say what's the probability density of being somewhere is to calculate the expectation value of the delta function of the coordinate. Essentially, I could say what's the probability of being in some region, and I can calculate the expectation value of an operator, which is 1 when my particle is in that region, and which is 0 when the particle is outside. But since I want to calculate in infinitely small region, I use delta function. So I want to calculate this. Let me skip the calculation. And because the answer is very simple and intuitive. Sum over A, CA squared, phi of Q minus lambda A absolute value squared. So if I plot this probability as a function of Q naught, what do I see? Suppose my initial phi of Q, let's say phi of Q was Gaussian. Suppose my phi of Q is equal to 1 over pi sigma squared. So it was a Gaussian distribution. And the square of it is also a Gaussian. And now the probability of finding my detector is, I should first mark the eigenvalues of the measured observable. And the probability is given by phi of Q. So it's Gaussian with all the widths are equal, all the widths. But the heights may differ, they depend on the state of my system. So I see that I prepared my system, I prepared my detector, I let them interact. Now, if I say, I don't know how to measure projectively my system, but I know that I look at the detector and it jumps to a state of certain Q node. I find my detector in some Q node and there is probability to that. And the probability is localized next to the eigenvalues of my observable. Now, if sigma is very small, then the width of these Gaussians is very small. And I only find my detector in states corresponding to the eigenvalues of the observables. If my sigma is very large, so this is projective measurement. If my sigma is very large, the Gaussians are very, very wide. Wherever I measure my detector, I can measure it at any point. It's determined by the width and not by the eigenvalues, which are all localized in some finite region. So this is the limit of the infinitely weak measurement. Any questions so far? So what I've done is is a very simple thing in essence. I told you, you know the rule that you measure observable A when the system is prepared in a superposition of CA times A. You get the eigenvalues of A with probability CA squared. Now I told you, I forbid you doing that. I forbid you to measure the observable A directly. What I allow you to do is I allow you to take a detector, a particle with some coordinate, let it interact with your system, and then measure the coordinate of that particle. And what we see is that we can still implement exactly the same projective measurement. Is when sigma goes to 0, when I have a very narrow peak here, a very narrow peak here, a very narrow peak here, I know that I can measure detector only at lambda A3, or lambda A2, or lambda A1, which is the eigenvalues of my observable times the effective coupling strength. And the probabilities are given exactly by CA squared. But because we introduced this detector into our model, we have the degree of freedom. We can prepare it in a different state, not with sigma going to 0, not in an infinitely narrow state, but with some finite sigma, or even with a large sigma. And this may be good, maybe not good, but this gives us extra degrees of freedom to play with. Possibly we can do more with that. Before we go and do more, I want to check one last thing about this projective measurement. Okay, I told you that, okay, you can measure detector in a state corresponding to the eigenvalues, but this projection postulate has one more thing. It tells you after you've measured your detector here, after you measured A3, you know the system is in an eigenstate of that corresponds to A3. But now we're not projecting the system, we're projecting the detector. So what will be the state of our system provided we measure detector at some value of Q naught? Let's go and calculate this. This is actually simple. We say we project onto Q node, so we apply the projection onto Q node to our final system state. And this is Q node times sum over A. This Q node kills the integral, and I have CA phi of Q node minus lambda A times A. So what does it mean? It means that my system state has changed, and the way it has changed is determined by the way I prepared my detector. For example, if I had my detector prepared in a very narrow state, this function is only non-zero when Q node coincides with this lambda A. So essentially, if I measured Q node corresponding to lambda A3, this state only contains A3 and no other state. Are you fine with that?
Can you repeat this?
Can you repeat? So we say this was the probability to measure detector in state Q node. I'm telling, fine, that's the probability. It agrees with our expectations. But suppose we measured the detector in some Q node, in some particular value of Q node. I sent one particle in my Stern-Gerlach device and I measured it here. can I tell what the spin state of my particle is, provided I measure it here? So the answer is, I say, so my detector is now projected onto this state Q node. So the system detector state, the detector is in Q node. What about the system state? I calculate this projection, and I see that the system state is now this. It was sum over A, C, A, now changed into this. Now, if my phi is a delta function, now this is only non-zero when A corresponds exactly to the Q node I measure. Instead, if my phi has some width, it does not correspond exactly to the A I measure. So this implements, this is like sigma going to zero. This implements the projective measurement we know. If we prepared our detector in this state, all this complicated model simply tells us that, fine, we cannot get rid of the projection postulate, but if we apply it to the detector instead of the system, we recover the projection postulate for the system. We did not solve the problem of how does a projection happen, how does the wave function collapse happen. We did not solve that. But what we did, we introduced the detector into our picture, and since we can prepare a detector not only in this state, but also in the Gaussian state, and in fact in any wave function we need, we have an extra degree of freedom to play with. So we say, fine, some measurements are described by projection postulate. Now, if we put a detector, which we measure according to projection postulate, between us and our system, then we can expand the range of possibilities. You would still call it measurement, you still do something and read the detector, yet the probabilities of reading are different, and the system state is not collapsed onto the eigenvalue of the measured observable, but is deformed somehow. For example, suppose I take sigma going to infinity. Sigma going to infinity makes phi essentially constant. The constant is very small, but it's a constant. Which means that when sigma goes to infinity, from here I see I have equal probability of any detector reading. And from here I see whatever detector reading I get, my system state is unchanged. This is the ultimate weak measurement. I don't gain any information in a single run. And I don't change the system state by measurement. I can have a projective measurement, sigma going to zero. Then I know I will get one of the eigenvalues. And I know that after I measure the eigenvalue, the system state will collapse onto that. And now I'm interested in the intermediate regime, where I gain something and I change the system state, but not drastically. That's the name of the game, weak measurements. So I have some sigma. I gain only probabilistic information on what my eigenstate of the measured observable is. Yet I do not disturb my system that strongly. That's in a single measurement. What will happen if I do statistics? If I do statistics, if I do many projective measurements, I get different eigenvalues with the probability Ca squared, and I can calculate the expectation value of my observable, which is sum over A, Ca squared, A. I can calculate it with projective measurements. Now I do this complicated measurement with some detector preparation. Can I get this information? I do many measurements. I send many particles to Stern-Gerlach device, and I count how many particles have spin up, how many particles have spin down, so I want to calculate the average spin projection. Naturally, you'd expect that, yes, you can do that from Stern-Gerlach device. Does it work out in our model? Let's check. So let me go and calculate the average detector position I will measure. That's the expression. I could go and plug in and calculate everything in this expression, but I can do it without knowing explicitly the form of phi. I can shift this q by lambda a. So I erase it from here, and I add it here. Now, okay, I will use the form of the phi a bit. I know it's an even function. Q to minus q, phi remains itself. I define it that way. I could do differently, but this time I defined it this way. Which means that the expectation value of q is equal to 0. This integral, this is an even function, this is an odd function. The integral is from minus infinity to infinity. This integral is 0. Now this is a constant, so I can take it outside of the integral. This is an integral of the wave function squared. The wave function is supposed to be normalized. So what I get is sum over a, Ca squared lambda a, lambda, sum over a, Ca squared a, which is lambda times the average of a. So, wow. If I'm interested in the expectation value of A, I don't need to do projective measurements. I can take any sigma, or I can actually take any even wave function of the detector, and the average position of the detector will tell me exactly the average position, the expectation value of my measured observable, multiplied by the effective coupling constant. So this comes perhaps as a surprise. We see that each individual measurement, when we take some sigma, each individual measurement doesn't tell us, okay, it tells us something, it tells us some probability, but it doesn't tell us rigidly that, okay, your system is in this eigenstate of the observable. No, it doesn't. Maybe it tells us some probability, but it doesn't tell us that it's this eigenstate. But if we do many experiments, we average, and we get the expectation value. You can already see some use in that. If we take a large sigma, we do not perturb our system that much. So we can measure our system that way many times. In each run, we don't perturb the system much. average over runs, we know the expectation value of the observable. But the system continues almost unperturbed. So we can watch quantum evolution without disturbing it. Sounds good already.
Why it doesn't disturb the system?
Once more, I take some sigma. This is the back action of the system. So this is e to the minus q naught minus lambda a squared by 2 sigma squared. If I take large sigma, larger, if I take that lambda a is much smaller than sigma, then for any reasonable new node, which is not larger than sigma, these functions are more or less the same. The values of these things are more or less the same. Which means that this state is almost the same as the original state. There has to be a price. We kind of learn whatever we want about the system without disturbing it. Either it is a great discovery or there has to be a price. But before the price,
can you explain? Do you mean the measurements of the same system, one after another,
no, I
repeated, or independent measurements of in a repeated experiment?
Repeated experiment. I prepare 1,000 copies of my system in exactly the same state.
Initial state, with the same initial state?
Yes, with the same initial state. Each of them I measure with a separate detector, and on average I get the expectation value, but each of them individually I did not disturb much. And that exactly touches the question of the price. Because, okay, in the projection postulate measurement, I measure each of the A's in each run I measure one value of A. I don't, and the access to probabilities, as I run the measurement many times, and I count how many times I got A1, how many times I got A2, how many times I got A3. And the average gives me this average. This is a statistical process, Russell probabilities, so I can get fluctuations. The fluctuations of my estimate for the average are given by this quantity. Not exactly this quantity, I'm actually interested in the standard deviation. But for that, let me first calculate this. I know how to calculate it. Squared A squared. Then I can calculate this quantity, and let me simply call it delta A squared averaged.
Doesn't it mean that if we make sigma to be large,
yes,
we need to make
a greater
number of measurements to define to determine the mean?
Exactly, it does mean that. That's what I'm trying to tell. So I have some standard deviation, and I know that my estimate of the expectation is going to have an error. I do n measurements. I get some points at A1, A2, A3, A1, A2, again A1. I do n measurements. I estimate the average A to be sum over measurement outcomes divided by the number of measurements. And I have some statistical error. And the error can be estimated as the variance divided by n and taking square root of it. That's the standard thing you know from the laboratory works here, that you make n measurements, the error goes as 1 over n, and there is some variance which characterizes the measurement. So I want to know what's the variance of my Q. And I will spare you the exact calculation. I will simply tell you the result of the Q square average is equal to sigma square over 2 plus lambda square average in square. And that means that the average delta Q is going to be sigma square over 2 minus plus lambda square delta A square. Because the average Q square is exactly lambda times average A. Which means exactly what this gentleman said, that if I take small sigma, the variance is determined by A squared. If I take a large sigma, I take a very weak measurement, I don't want to perturb my system much, my variance will be much, much larger. It will be determined by the measurement weakness, by the width of the detector state, not by the system state that much. So if I want to avoid perturbing my system, but still get some information, I need to increase the number of measurements. By how much? Well, what's the error of estimating average A? It's equal to the error of estimating average Q divided by lambda. And that is 1 over lambda square root of delta Q square divided by the number of measurements I make. And that's equal to 1 over square root of n.
Could you explain this first equality? Like why error of
So-
average A equals error of the average of
Let me
divided by
explain. So, do you agree that the error of average Q is this?
Yeah.
Now, average Q, I believe, is lambda times the average A. So I calculate the average Q, and I should divide it by lambda. I had an error in determining average Q. I divided it by lambda to determine the average A. I should divide the error as well. So once more, we see that if sigma is small, the error is determined by the system state exactly here. We reproduce the projective measurement. But if sigma is large, the error is dominated by this, and it's much, much larger than we would get with projective measurements. So to get the same accuracy of the estimate, we need to compensate for this by increasing the number of measurements. One important lesson we see from this formula is this. We talked about lambda, we talked about sigma, but we see that the actual error is determined by the ratio of lambda versus sigma. I don't care how wide my detector distribution is. I don't care how strongly it is coupled to my system. What I do care about is how large the shift is compared to the detector state width. And that's what this tells us.
Don't we need the absolute, don't we need the relative value of
That's exactly the relative value.
why it's relative?
The shift
It's
is
the
lambda
absolute
A.
error of A. It's the absolute error of A.
You mean you want to calculate the relative correction to A?
Yes.
You can, and then yes, okay, this lambda enters. That's correct. That's correct. So that's true. But if I'm interested in the absolute value, in the absolute error, then it's only about the ratio. That's the weak measurement, and I'll make a pause here, give you 30 seconds to think whether you have any questions about what I told you, because that's the end of a chapter, and I'm going to switch to a new chapter now. Think for some time. Do you have any questions about what I told you?
Can you speak a little bit slower? Just too fast.
You mean not write, not move,
Just
but
speak. You
Okay.
write
I'll
fast
try.
and speak fast just in the same time. But it's sometimes difficult
to write down. I
to
see.
catch
I see.
both.
I see. Okay, I'll try it.
So just remember your colleague, yeah? His style was somewhat different. So
Okay.
make a shift to his style, please.
So, are there any advantages, or it's just a different approach to measure?
So far, we see, it definitely is a different approach. Are there any advantages? So far, we imagined there must be an advantage that we can measure the expectation value without perturbing the system much. So we can measure something else later. And in the next chapter, I'm going to tell you how measuring something else later allows us to measure something very, very different. Something new, something we possibly wouldn't be able to measure otherwise. And measuring that actually gives some advantages, and that will be the third thing I'm going to tell you today.
So advantages will relieve.
Yeah, the advantages will be revealed towards the end of today. Okay. chapter is called weak values. So what we did so far, we prepared the system in some state. We ran interaction of the system with the detector. We arrived at an entangled state of the system and detector. And then we measured the expectation value of the detector position. But we told that if we take a large sigma, we did not perturb the system much. So what we can do is we can try to do another measurement of the system now. So let's say measure B, some operator B, which is different from A. And we measure it projectively. I could introduce another detector with sigma equal to 0, but I won't bother. We saw that in the projective measurement limit, with the results with the detector coincide exactly with the results we get from the projection postulate. So I will simply say I apply projection postulate, I measure B projectively, and I get some values, B, I measure. And I get psi f tilde, which depends on B. If I calculate anything about the first measurement, it doesn't care about what I did next. It's not going to make a difference. Now I'm going to change the rules of the game. I'm not counting in all the measurement results. Saying, okay, I measured B projectively. I can get different eigenvalues of B. I'm going to keep only those measurement results here that give me some particular eigenvalue of B. So I prepare my system, I get some Q, and then I get some B1. Now I discard it. It was B1, I don't want to count any runs that gave me the eigenvalue of B1. I only want B0. If the second measurement gave me B0, I keep it. I write down all the results and I average over them. All the results that gave me anything but B0, I cross them out. That's the rules of the game. That's called the weak value model. And now I want to ask, what is the expectation value of Q of my detector, provided that I measure B0? So how do I do that? I know before the second measurement my system state was psi f. Now I measured B and I got B0. So I have to project the result onto B0. And this is my psi f tilde of B0, but I'm going to omit it. And now what I want to know is what's the expectation value of Q, my psi f tilde.
B0 essentially means sum over B0 and all values of Q.
Yes, yes. It means identity in the detector space, yes. have an explicit expression of psi f tilde. Let's go and calculate that. I still have my psi f. So I simply apply the projection. This is equal to B naught. And sum over A. Integral to Q. CA B naught A. Phi of Q minus over A. Q. So I have a very much explicit expression, except for it doesn't tell me much. So I'm going to go one step back. I'm going to remember, oh, I calculated psi f like this. Was my initial state, detector initial statement was this interaction operator. So I have B naught, minus I lambda A D times psi I times detector initial operator. Now I tell you, I'm only interested in weak measurements, because the second measurement only brings me no trivial information when my system was not perturbed. If I projected my system, I know what the outcome will be. I know I'm in a state with some A. I know what B node I want. What do I learn? So I want the weak measurement, not the projected measurement. So I want lambda over sigma much smaller than 1. And let me say that this actually means that lambda is small. If I assume this, I can expand this exponential. Say that this is approximately equal to B node B node 1 minus I lambda A B psi I I. So far it is trivial, just expanded the exponential. Now I will use the fact that A only acts on my system. So I can say that this is equal to B node times B node psi I times 1 minus I lambda B node A psi I B node psi I P times di. When I use identity, I have B node psi I, and here I get the matrix element that I want to take identity out of the parentheses, so I divide the matrix element by this scalar product. And then I use this identity again. saying that this is approximately B node psi I times exponential minus sine lambda B node A psi I B node psi I P Ti. Okay, I know what this guy does. It shifts my detector by this number. So, what I expect for the average of Q is lambda B node A psi I divided by B node psi I. I expect something like this, don't you? Except for, there is a problem with this expression. Q is a Hermitian operator and it has real eigenvalues. Whatever I measure about Q, it's real. Whatever I average, it stays real. Now, this thing is not necessarily real because with the standard expectation value, I take complex conjugate, it's equal to this, but my A is Hermitian, so it's equal to itself. Here, if I take complex conjugate, my A is still Hermitian, but I switch the roles of psi initial and B node.
Could you please show explicitly how have you got this expression?
This one?
No, like to the right. Yes, because
I got it here.
Yeah, that I understood, but where is normalization? Where is
the normalization? Okay.
For me, it's not clear how.
I understand. Let me try to give you the intuition. I haven't taken care of normalization and I didn't treat things carefully yet. I wanted to rely on intuition. I know that an operator like this with a number here, it shifts the detector state by the number. So my detector initial state was a Gaussian with mean 0. Now I apply this operator. I simply shift the Gaussian by the number next to the P. So if my mean was 0, and I shifted the Gaussian, I expect my mean to be exactly what I shifted it by. However, there is a problem, and the problem is that this thing is not a real thing. So I took my wave function and I shifted it by a complex number. Not by a real number, but by a complex number with an imaginary term. So let's have a look in detail at what happens here. I'm going to take and apply this operation. I'm going to denote this as zeta. And I want to calculate what is e to the minus I lambda zeta p times the detector initial state, which is integral to q, phi of q, q. What I can do is I can separate the real part of this thing and the imaginary part of zeta into separate separate terms. And the real part of zeta does exactly what I wanted to. It gives me integral dq phi of q minus lambda, real part of zeta. But the imaginary part stays here. And it looks like a translation. It's still kind of a derivative, but it's a translation exactly by the imaginary number. So I don't really know how to understand this state shifted by an imaginary number, but I know that I can translate it here. So I can say that this is integral dq phi of q minus lambda zeta q. But now I have to remember that zeta is complex. And I want to know what the wave function is. So phi of q is equal to e to the minus q squared over 2 sigma squared. And forgive me not writing out the normalization. Okay? And forgive me not. So phi of q minus lambda zeta is exponential of minus q minus lambda zeta squared by 2 sigma squared. This is equal to e minus q squared minus 2 lambda zeta q plus lambda squared zeta squared divided by 2 sigma squared. This part I don't really care about. It's a factor. It will be taken into account when I renormalize things. So I drop it, not that it shouldn't be there, it's just, it doesn't change the dependence on Q. So this is the minus Q squared. Now here I have the real part, and I have the imaginary part. Let me separate them. Let me say this is e to the minus q lambda real part zeta square. And here I have the imaginary part, which I don't put into the square. So I get plus I lambda imaginary part zeta over sigma squared q. And this very much looks like e to the minus q minus some average q squared plus some average momentum my wave bucket has. So this way, when I consider things more carefully, I see that my expectation of q should be shifted by the real part of that expression, of that zeta. And the imaginary part contributes to the momentum. Still, I cheated in this calculation. There is no such thing as a state of q with imaginary component, and I used it at some point. So I'd rather like to do an honest calculation and calculate the expectation values appropriately. So let's do it. So let me forget about this last step. This is my final state with the tilde after I post-selected B to yield me B node. And I want to calculate this. So I want to calculate this. B node here and here give me 1. This gives me B node sine I squared. And here I have di 1 plus I lambda zeta star P Q 1 minus I lambda zeta E
I still don't understand why you expect the normalization. Like our projection.
Oh, yes. Of course, I need to divide it by psi tilde f. Psi tilde f. Thank you. So this will be B node psi I squared di 1 plus I lambda zeta star B 1 minus I lambda zeta E di. Right, this is the correct expression I should be considering. Let me focus on the numerator first. I want the leading order in lambda. I assume that my detector system interaction is small. So I want the leading order in lambda. Let me try the leading order, the most leading order I can. I take 1 from here and I take 1 from here. Well, then I need to calculate the average Q on the detector initial state. And it was 0. I prepared the detector state in the Gaussian. So 1 gives me 0. So let me go to the next order in lambda. What I want to calculate is di I lambda zeta star B Q di minus I lambda zeta di Q B di. This I can express as this. I simply use the commutation relations. So this is and this is actually easy to calculate because what I want is integral dq phi star of q q minus psi dq phi of q. This is equal to this, so it's easy to take derivative. When I take the derivative, I simply get I q over sigma squared times 5q. So essentially, what I want to calculate is I divided by sigma squared, the average q squared. The average q squared is sigma squared over 2, so it's I over 2. So this is I over 2, and this is by I smaller, so this is minus I over 2. So I get lambda zeta plus lambda zeta star divided by 2, which is lambda, the real part of zeta. That's the leading numerator contribution here. The leading denominator contribution is with ones. I take 1 from here, I take 1 from here, I get di times di. This is 1. So this is 1, and if you think carefully, also up to lambda squared. And this cancels. So this expectation value is lambda, real part of zeta. So it turns out that my cheating calculation was correct, at least to this accuracy. So now, after we've done all the math, and just before we go for a break, let me reiterate what we did. We took a protocol that we measure a system weakly, and then we measure the system strongly, and post-select the results of the strong measurement we like. And the probability of post-selection, since the first measurement is weak, it's not supposed to disturb the system. We'd expect that the second measurement, the probability the second measurement yields B node, is the scalar product of B node with the initial state squared. And indeed, we see that the probability is like that to the leading order. And then we asked, on this post-selected set of experiments, what's the average Q? And it turned out to be this, and zeta is B node A psi I, B node psi I. It's not an expectation value, it's something completely different. It's called weak value
Without taking real part.
without taking real part. Yes, for now we've seen how to measure its real part. From my cheating exercise, you can anticipate that we can measure its imaginary part by measuring momentum. We'll see that after the break. But the whole thing is called weak value, and so what we managed to do is we managed to define a protocol that allows us to measure something different from an expectation value. So I guess that's a good place to stop and digest it. And so let's go for a break.